Hello viewers, in my last lecture I had started a reaction which is going to be very important in food industry, and that was that when we talk of bread or brioche or cookies and biscuits, we find that their crust is golden brown and they have distinctive flavor. That means roasted and baked foods have distinctive flavor. Not only this, if you talk of roasted steaks, they give us a special aroma and flavor. On your screens you can see steaks which have again a golden color, and you can also see potatoes which have a golden brown color in them. And we can also talk of baked potatoes. When we talk of baked potatoes and we heat them to a very high temperature, say 500 Kelvin, they have a special smell and special taste. And what you find that they have been baked. What happens during the process of baking? So what we find that in the process of baking, the carbohydrate sugars react with amino acids, and under the pressure of heat we get baked brown foods its distinctive flavor. And this interaction between the carbohydrate and the amino acids present in the food at high temperature is known as Maillard reaction. See, on your screens you can see that it is written Maillard, Maillard reaction, but Maillard is not pronounced as Maillard. You have to remember it is pronounced as Maillard reaction. And this interaction that is between the amino acid molecules and the sugar molecule is non-enzymatic. And since it is non-enzymatic, the browning reaction occurs rapidly at high temperature. That means now this browning is occurring due to interaction between the sugar molecule, the amino acid, and what we need here is high temperature. So this reaction will take place. And what I have already said that in this reaction the sugars react with the amino acid, and at high temperature they form a complex mixture of poorly characterized molecules which are responsible for the range of flavors and aromas that we get. And you will be surprised to know that if a food is containing fructose, it will undergo Maillard reaction more rapidly. Why so? Because in the initial stages of the Maillard reaction occurs more rapidly with fructose than with glucose. Why is it so? Because fructose used in Maillard reaction exists to a greater extent in the open chain form than the glucose. So it reacts easily with the amino acids at high temperature. Now another reaction of fructose which is very important is the dehydration reaction. That is, when fructose is heated, it dehydrates rapidly to give us hydroxymethylfurfural. So this hydroxymethylfurfural is not only given by fructose, it can also be given by other reducing sugars, but fructose gives us the most. It dehydrates very rapidly. And this hydroxymethylfurfural, which is also known as HMF, is a white low melting solid which is highly soluble in both water and organic solvents. So when is this HMF formed? It is formed when sugar containing foods are heated or cooked. So imagine when we are heating our food and it contains reducing sugars, they will form HMF. So, and we also use this HMF as a food improvement agent in food industry, and it is being primarily used in the food industry in form of food additive. It increases the shelf life and it increases the taste of the food. Now, as you can see on your screens, we have started with fructose. Now, when we talk of fructose, so what happens? It undergoes dehydration. And when it undergoes dehydration, what we find, this OH undergoes protonation and it is converted to OH2 positive. This is removed as a water molecule, and at the same time a hydrogen from this alpha hydrogen is removed from here. You know that this alpha hydrogen is acidic because it is attached to a OH group. So, and this molecule now tautomerizes into its enolic form, right? And when it tautomerizes into enolic form, and this is the enol, we get an enol which then tautomerizes to convert into an aldehydic form. And this molecule will undergo this series, this intermediate will undergo this steps again will take place here, and it will result in the formation of HMF. So as you can look at the structure of HMF, HMF contains a hydroxymethyl group here and a aldehydic group here. So this is what is HMF. So that means when we are heating a food, the fructose which is present in the food loses 3 water molecules and is converted into HMF. Not only this, now this HMF can also be converted to 2,5-dimethylfuran, which is DMF. And you know that DMF is a potential biofuel with a higher energy content than bioethanol. That means now we can prepare now from fructose. That means we are preparing it from a source which is naturally occurring. That is, we can say that this will be a renewable fuel. That is, we are not obtaining it from petroleum. That is, HMF which we've obtained by the dehydration reaction of fructose can be converted into 2,5-dimethylfuran, and this 2,5-dimethylfuran is a very good biofuel. That is, when I say it is a potential biofuel, what we mean here is that we can use it and in future, because its energy content, that is, it will liberate more energy when we compare it to bioethanol. And now you know that we are having vehicles which are having blended fuel in them, that is, they are running on mixture of petrol and bioethanol. Now I would like to discuss the properties of fructose in which it is similar to properties with glucose. As I had already said that glucose and fructose have the same molecular formula, which is C6H12O6. So that means they are functional isomers. In glucose, we have the aldehydic group, that is CHO group, and in fructose, we have a ketonic group. So a fructose is a ketohexose and glucose is a aldohexose. And what we find that these two molecules differ in configuration at only first 2 carbons. That is, this is a CH2OH, whereas in fructose, in glucose we have a CHO group, and then at second position in fructose we have a ketonic group, that is the carbonyl group, and here we have a secondary alcohol, that is CHOH group. Whereas when we compare the configuration of glucose and fructose at the 3rd, 4th, 5th and 6th carbon, we find both have the same configuration. So what we can assess from here, or we can say that maybe fructose has similar properties to glucose with slight modifications. Why is it so? The second point that we have to keep in mind, that when we carry out the reaction in a basic medium, fructose undergoes epimerization and enediol rearrangement. And if we are dissolving, we are taking glucose in alkaline medium, in basic medium, glucose also undergoes these rearrangements. So what we find that when they undergo these rearrangements, this rearrangement mechanism I have discussed in great detail in one of my lectures, that is monosaccharides 4 on fructose, whose link is also given here. We find that both glucose and fructose give us the same enediol intermediate. And now this enediol intermediate, if it tautomerizes at C1 carbon, it will give us glucose, and if it tautomerizes at C2 carbon, it will give us fructose. So that means in basic medium also they have the same structure, they go through the same structure. So what we find that in basic medium we can have a mixture of D-glucose, D-mannose and D-fructose, and in brackets I have shown plus plus glucose, plus mannose, and here minus fructose. So what does this D indicate? That this molecule is dextrorotatory, fructose is levorotatory, and mannose is again dextrorotatory. But all the three molecules have the same configuration, that is they have OH on the right hand side at the highest numbered asymmetric carbon. And the second point that you're finding here, that all the three molecules, that is of glucose, fructose and mannose, they differ in configuration only at the first two carbons, whereas the configuration at the 4 carbons is same. But here I would like to point out that the configuration, when we are comparing configuration of glucose and mannose, so they are, what are these? These are C2 epimers, that is they are differing in configuration at C2 carbons. So these have different orientations or different configurations at the C2 carbon, and the configuration at rest of the 4 carbons is same. So if the configuration is same and they are interconvertible in basic medium, and they differ in configuration only at C1 and C2, so we can say that glucose and fructose will show similar chemical properties with slight modifications. So let us now discuss the chemical properties of fructose one by one. The first reaction is that the fructose can react with HCN to give us cyanohydrins. And what we find, I have again discussed the mechanism of this reaction in great details in my lecture on monosaccharides 1, that is properties of glucose 1, whose link also I am sharing here. So you know that this carbonyl group, that is the ketonic group here, is planar in shape, it has a planar structure, and then this carbon is electrophilic in nature. So CN will make a bond with this carbon and H will go to this oxygen. And since the structure is planar, that means the CN can attack from either of the sides. The reaction can take place from either of the face of the ketonic group, as a result of which a new center will be, a chiral center or an asymmetric center will be generated, and we will get epimeric cyanohydrins. Now the next very important derivative, and on which you are often asked the mechanism of reaction, that is ozazone derivative. And what we know, that D-glucose, D-fructose and D-mannose form identical ozazones. Now why do they form identical ozazones? Because the ozazone formation involves only carbon number 1 and carbon number 2. Right, the rest of the 4 carbons are not involved, because we have a special type of rearrangement in these reactions, which is Amadori rearrangement, and this Amadori rearrangement does not occur beyond C2 carbon. So that means the configuration will be same, and I have discussed the mechanism of glucosone formation, that is ozazone of glucose, in my lecture on monosaccharides 2, that is properties of glucose. So if you look into the structure, so this is what I was trying to tell you again, and I've told you before also, that these two are only differing at these 2 carbons. 1 2 1 2 1 2, and since they're differing at only these two carbons, and the reaction will also take place at these two carbons only, right? And these four carbons, these four carbons which are below, are not involved in the reaction. So as a result of which, whether we carry out the reaction of glucose with phenylhydrazine, fructose with phenylhydrazine, or D-mannose with phenylhydrazine, we will get the same ozazone derivative. We'll be using excess of phenylhydrazine in this reaction. So what we find here, that glucose reacts with fructose reacts with 3 molecules of phenylhydrazine to give us phenylhydrazone. So I'll just quickly revise the mechanism here, that the first step is the condensation reaction. So when I say first step is the condensation reaction, what happens, this oxygen and this H2 from here is eliminated as water molecule, and what we get here is we get a hydrazone. And then in next step, Amadori rearrangement takes place, and what happens is in Amadori rearrangement, that this nitrogen is more electronegative than carbon. So what happens is that these pi electrons move towards this nitrogen, and as a result of which the bond between this carbon and hydrogen will break, and we get a double bond here. Now since it has a negative charge here, this H will make a bond here, and what are we getting here is we are getting a enol form. This is the intermediate that we are getting. Now what happens in the next step, you will observe that this oxygen, this is more electronegative, so oxygen will pull the electrons towards itself. The bond between oxygen and hydrogen will become weak, so this will go here as a double bond. So what happens first is that this nitrogen is more electronegative. This will now pick up a proton from here. This bond is picking up a proton, and a result of which that this bond now makes this electrons, the bonding pair of electrons, move here to form a pi bond between carbon and oxygen, resulting in the formation of an aldehyde group. And this bond, that is the bond between carbon and carbon, will move on here to give us this intermediate. This is the next state in this structure. And what we observe here is that the first molecule of aniline is eliminated. Now this intermediate will react with the second molecule of aniline, and when it reacts with second molecule of aniline, here again it is a condensation reaction in which this oxygen and H2O is removed as water, and we get this intermediate. Now this will react with the third molecule of aniline, and this NH2, being basic in nature, will pick up a proton from here, and ammonia will be eliminated here, and a bond will be formed between this nitrogen and this nitrogen, resulting in the formation of ozazone derivative. So if I summarize this reaction, first reaction is condensation reaction, then is the Amadori rearrangement, in which it reacts with aniline here, and we get this, and then we are getting this, aniline is eliminated here, we get this molecule which again reacts with the second molecule of aniline to give us this product, which then reacts with the third molecule. This here again is a condensation reaction, which then reacts with the third molecule of aniline to give us ozazone. So we can say what happens in the first step, the ketonic group is reacting with phenylhydrazine to give us an intermediate which undergoes Amadori rearrangement, in which the CH2OH group is oxidized to a CHO group. So what is the result of Amadori rearrangement? We are oxidizing this to CHO, and then again ultimately a condensation reaction takes place to give us this intermediate, and then we are getting here the ozazone derivative. So what we find, that since in basic medium, whether we dissolve glucose, fructose or mannose, since the reaction is carried out in basic medium and only the first and the second carbon atoms are involved in the reaction, we will get the same ozazone derivatives. But please remember, these ozazone derivatives will have characteristic melting points from which we will be able to distinguish between glucose, fructose and mannose. In my next lecture, now I will be discussing the remaining reactions of fructose, that is the oxidation reaction, the reduction reaction, and how are they different from glucose, that is where is their similarity between the reactions, that is the oxidation reactions, and where is the dissimilarity, not exactly dissimilarity, that what happens when we carry out the reduction of glucose and fructose, why are we getting little different products. Thank you.